let's start with the next lecture, that is this point processing. So point processing, so a point is, it refers to a pixel, so you have an image to take one single pixel, and then point processing transforms that pixel into another value. So the value of the pixel transformed to another value. And with this, you can construct several useful operators. This brightness and contrast adjustment, gamma correction, histogram equalization, histogram matching, color correction. So we will see all of these. So here you have the final results. We will see how to do each one of these operations. But you have the original image here, and then you can decrease the contrast or increase the contrast. So the contrast is the difference between the minimum and maximum values in each one of the channels. You can increase the brightness or decrease the brightness, increase gamma or decrease gamma. We will see what gamma is. You can do operations with the histogram. So this is the kind of results that we will get. Okay, so in general, you have an input image. For every pixel in that input image, you go through a function, and then you have an output pixel. And this is the same with different things. Okay, so then, in general, you have an input image, you go through a system that will transform your images, and then you will have an output. And this system will simply, so the output image will simply be the input image going through the function, and that function can be linear, can be non-linear, can be whatever. And what is important is that that function only depends on the current pixel. Okay, so this pixel will transform into this one in the same location. So the location stays the same. And somehow this is reflected here. Okay, so the coordinate RC, you have some value I, the input, then you go through the function, and then you store it again in RC. And if you have only one band, then this function can be, so it is one of them, or some function. But if you have multiple bands, then you can do two things. One is to apply the same function to each one of the bands. That is the first choice. The second one is you apply a different function to each one of the bands. So each band has its own transformation. And yeah, there is nothing. Yeah, what is here is that function is nothing more than a lookup table. So lookup table, let me do some drawing. Okay. Okay. Okay, so it is a lookup table, and that also happens for, I don't know, let's say that you have a function x, you have y, and y is 2x, let's say, and then if this is from 1 to 10, this goes to 20, and then it is this line. So what it means is that you have a table that makes correspondences, so that to value 0, you have 0, to value 1, you have 2, value 2, you have 4, value 10, you have 20. And maybe you can even write it for 1.5, 2.2, or whatever. So you have a correspondence between two values, and the argument can be continuous or discrete. But what is important is that for every input value, you have only one output value. And you may give, so the function is this is a function, it is a list of pairs of numbers that are related. And this is also a function. In this case, it is the same function. It is because we are too lazy and we don't want to write the whole table. And then we give the equation so that if I give you x, you can compute y. but actually a function is just a lookup table. So anything that you can write as a lookup table is actually one of the functions of the kind that you can use to transform your images. So this is the connection here with the lookup tables. And lookup tables, they are also written like this, LUT, lookup table. Okay, good. Then this +1 comes from MATLAB. Okay, so that in MATLAB the index is start at 1. So this is index 1, this is index 2, 3. So if I want to get the value at 0, I have to access this table at the location 0 + 1. But okay, this is a MATLAB thing that we don't care at this moment. Okay, so yeah, this is what I just said. So a function is a lookup table, and then for every input value, you remember our images were with 8 bits, they are between 0 and 255. Then if you have any value in the input, you go to the lookup table and substitute by the value that you are given in the table. So this 127 would be substituted by this value. Okay, so we don't have it here, but 103 by 69 and so on. And here there are a few things. This is our function, and we will give more ideas about the shape of this function. But we see that it is different from this diagonal line. The diagonal line is the identity transformation, so it is no transformation at all. So here we see that we are below identity where we are above identity. Okay. And for instance, you can be lazy to write the table, and then you may give a function. And one of the useful functions is this sigmoid. The sigmoid is a function that has a few parameters. Here you see 255, 127, 32, and each one is controlling something different. So the 255 controls, so this function is defined between 0 and this value. So it will go from 0 to 255. And then this thing here, the 127, tells you at which point you are going to have the maximum value. So this is the maximum value, at which point you are at half the maximum. Why half the maximum? When x takes the value 127, this is 0, e to 0 is 1, and then you have 255 divided by 1 plus 1, that is 2. Okay, so this is the point at which the sigmoid goes to half the maximum. And this a and 32 actually could be just a. It controls how fast you go from, so the sigmoid goes from the minimum to the maximum. At this point, it goes half maximum, and then how fast you go. So do you go very slowly or do you go very abruptly? Okay, so this is controlled by this element. Okay, so this is the sigmoid function, and you see how it is used. It is used to construct the lookup table. So we have all the values here. So we have the column of x, and then we are calculating the columns of y. And this is the same. You can use the same lookup table for all the channels, or a different lookup table for each channel. Very good. So then let's say that this is our transformation, and then we take this image, we apply the same transformation to all the channels, and then we will get this one. And we will describe these kind of functions even in more detail later. Any questions to here? This is very easy. Okay, so now let's go for some more examples. Let's say that we have this image. We split it into the 3 different channels, red, green, and blue. And now we apply a different function, a different transformation to each one of the channels. So to the green channel, we will apply this one to the blue channel, and this one to the red channel. Okay, so here we have the results. So the results is this one here, the red one. So the red one, many of the low values, we are even making them even lower. So it will be darker than it was. Compare how the red was and how it is now. So many regions are even darker. The same happens here. So many regions are even brighter. So compare all these, we are saturating. Now you know this word. So we are saturating. What about the green? So the green, whatever was dark now will be bright. Whatever was bright now will be dark. Okay? So see, so the thunder was bright. Now it is very dark. And then for the blue channel, we are kind of doing the two effects at the same time. So for half of the range, so for the dark values, we are making them even brighter. And for the brighter values, we are inverting them. So if you are very bright, you will be very dark. So for half the range, we increased the contrast. For the other half, we are inverting this negative slope. It's called inversion of the contrast. So whatever was white becomes black, and the opposite. Okay, so this is the result now for the blue. Now you can combine the three channels into a single image, and we have this one. Okay, so then we may wonder, is it exactly the same transformation that is it the same information that I have in this image than this one? What do you think? So if it is the same information, I should be able to recover it. So given this one, I should be able to recover this one. Do you think we can recover or not? Yeah. Yes. So you simply have to invert the function, right? So now y, so you transpose this. So y would be horizontal. So you give me y, I tell you x. Everybody agrees. Yeah. So in general, yes. In this particular case, no. If I tell you that y is 150, you don't know which was the original value, because it is not a function. It has two x values are mapping onto the same y. So to be invertible, the function has to be 1-to-1. So in Spanish it is called biyectiva. So,
but if you apply the lookup table, like the inverse lookup table to each of the channels, you can invert it, right? If you already know one.
But the blue one you cannot invert. The other two you can invert, forgetting about the saturation. So if the saturation, you have the same thing. So I see 255, and I don't know if it was 255, 254, 253, because they all map to the same point. But forgetting about that, this would be almost invertible. This is clearly invertible, the green one, but the blue one is not invertible. No?
I don't get why.
So if I tell you, so do it this way. This is the definition of one-to-one function, bijectivas. No? So I have here x, have here y.
Oh yeah, I get it. So
You get it?
yeah.
Okay, so. Okay, so to keep the same information, f has to be invertible. And f here, the blue one, is not invertible. Okay, then yeah, some examples of these kind of operations. Now we will see each one of them. So we have an image, we compute the luminance histogram. So you already know what the luminance is, what the histogram is. So that is the histogram of the luminance of that image. And then we will, the first operation we will see is this increased brightness. That was one of the operations in here in the catalog, okay? So increased brightness, it is simply, you give me a value and I will shift that value up. So I will add a positive value, so G, so that all the values, all the gray values go up. So somehow this is identity, I don't do anything. So if you tell me value 0, then I will return 60. And if you give me 10, I will return 70. I'm adding 60 all the time. And that goes well up to here. Beyond this point, plus 60 goes above my capacity to represent numbers. So this fact is called overflow. So if you take 250 and you add 60, then you are overflow in 8 bits. So you have to saturate, or you have to do something, and the typical thing in images is saturating. Okay, so this is this idea of saturating. So it is the image plus something. If that something is smaller than 256, or you saturate the value if it is larger than 255. Okay, and the histogram, this is the result of increasing all the brightness of all channels, and we see that there is some saturation as expected from this transformation. Okay, we can do the opposite. So we can subtract some value, some positive value, and now you will have to saturate on the left. So the low values, if you have 10 and you subtract 60, you are having a negative number, which in unsigned integers with 8 bits you cannot represent. So you have to saturate. Then you saturate to 0, and then you have saturation here. Have we lost information with these two transformations? Do we lose information or not?
The brightness or the darkness pixels, right?
Sorry?
For example, in this case, we will lose the darkest pixels.
The dark values, yeah. The dark values, we are losing them because we are saturating them to 0. And then if you want to invert, you don't know which one was, so you see a 0 in the output, but you don't know what was the original value. So you have lost information. So always that the function is not invertible, you are losing information. And this function is not invertible. This function is neither invertible. Okay, then contrast. So the contrast, I defined the contrast before as the difference between minimum and maximum. So we have the identity transformation there, and then I may define this line. So let's say that my original image could completely occupy the input range. So it was going from 0 to 255, really. And then I apply this function. My output will not go from 0 to 255. It will go from 60 to, I don't know, 200. Okay, so the difference between minimum and maximum, now it is smaller. So having a smaller difference is having less contrast. And also something noticeable here, and that is the characteristic of this kind of transformation, is that the slope of this line is larger or equal or smaller 1. How is that slope? Smaller than 1. So the slope is smaller than 1. So that is the characteristic of decreasing contrast. Something is decreasing the contrast if the slope there is smaller than 1. And this is the equation. Okay, so the equation is nothing really fancy. So you apply a shift, then you multiply by something and you add that shift. The shift here in this example is 127. But this structure here So you subtract something, then you do something else, and you undo what you did. This is something very common in English and in mathematics in general. That is, let's say I want to do some transformation. So I have here this x and y, and I have this is identity. So this is I have x, that is x. So that is identity, and I want to construct this line. So I want to construct this line around this point. So what I will do is I will define a new axis. I will define this new axis. So this will be x prime, y prime. And how do you get to x prime and y prime? So y prime will be y minus y0. X prime will be x minus y x0. So this is the point x0, y0. And then you define your function in terms of x prime and y prime. So you say y prime is a x prime. And now you undo your transformation. So this is y minus 0, a x minus 0. Then this is a x minus 0 plus y0. And in the slide, these two values are the same. Okay? But in general, this is something that we do all the time. So either a shift of the coordinate axis, like this, and in many applications, you also do a rotation of the coordinate axis, so that you rotate in some way that the y rotating and shifting and all that, because this transformation in the new space, it is very, very simple. This doesn't look so simple. It's not so difficult either, but it is not that as simple. But this one is extremely simple. So first you make a transformation of the coordinate axis, you define a simple transformation, and then you undo it. This is same as we have there. Very good. Then next operation will be increasing the complex. So now, instead of having a slope smaller than 1, we will have a slope larger than 1. And then we have to be careful with the saturation. Yeah, so we see that we are saturating on both sides, the dark and the white one. This is the transformation, and then the transformation is very simple. So it is, if the transformation is smaller than 0, you saturate. If it is larger than 255, you saturate, and then otherwise you keep it. Okay. Then let's look at the original histogram. So the original histogram, yeah, here. So the original histogram of the input image, we see that it starts at value 40, let's say. So there is no pixel here with 0 value, with value 1, with value 2. And here there is no pixel with value 255, 254, 253. So that somehow is not taking advantage of having all this dynamic range. So you were given 255 beams or 256 beams to put your pixels, and you're not using all of them. So why don't we use all of them? So why don't we stretch this histogram so that it really goes from 0 to 255? So this is what is done here. It's done here. So let's say that you have discovered that this is the minimum value in the input, this is the maximum value in the output, and then you want the minimum value to map it to 0, and the maximum value to map it to 55. And in general, can do it this way. So let's drive this. So you have an image, it goes from, goes from minimum of I, maximum I, and we want it to go to minimum of J, but we will set it to 0, and to maximum of J. So we want the equation of this line. So this is X, this is Y. Okay, so how do we do this transformation, which is the equation of that line? So let's try again. So if I shift my Y, so actually here you see the trick that we were doing before. We are setting the coordinate axis here. So this part corresponds to the change in coordinate axis. And then in this new coordinate axis, what is the slope? So the slope is mj minus mj divided by mi maximum minus minimum. And then you can rewrite it. I is mj plus, and then this thing. This is what is in the slide. So in the slide, that is what we have. Okay, so this transformation is very important, really, really important. It takes something that is between some minimum and maximum and maps it to something that is between a different minimum and a different maximum. And you can control the output, which is the minimum and maximum for you. So, yeah.
We have to learn the formula.
In general, no. This one is extremely important. And in general, no. Yes, no. In the sense, this one is really, really simple.
Yeah.
So all the simple formulas we need to know.
Like we have to know, or we have to like start from 0.
As you want. But you need to know the final result. So either you know how to get the path, or you learn the final result. So this one is extremely important. And does it have a slope larger than 1, smaller than 1? How is the slope of that transformation? Larger than 1, always, or only in this example? Always. Because the minimum will be somewhere here. In the worst case, will be 0. The maximum in the worst case will be 255, and then the slope is 1. So it always has a slope that is larger or equal to 1. Okay, then we can think of the following process. So I can, for instance, given an image, I can increase the this is the original contrast. I can decrease the contrast. Okay, so we know how to do that now already. So we put a slope of 0.5, and then I can restore the contrast. So I can restore the contrast. So here my factor was 0.5. Now I put a factor 2, and then it will expand again the contrast. But now this is with low contrast, and this is the restored contrast that we don't see here. Okay, so but what we see here is that we have some holes in the histogram. Why do you think we have holes in the histogram? Let's consider some value here. Okay, so I will do it with a small value. Okay, so let's do it correctly. Don't try to do anything strange. So let's say that my transformation. So I have an image, then I will reduce the contrast. So multiply by 1/2 the contrast. I will have a new one, and then I will construct a new one that is multiplying by 2. And the full formula was something like this. J is equal to 1/2 and 20 1 minus 127 plus 127, something like that. Okay, so the idea is you take the difference to 127, you multiply by 1/2, and then you add it back to 127. So let's study what happens around 127. So 127 goes through this function, and then it goes to 127 again. You agree? Because this is 0, and then 0 times 1/2 is 0, plus 127 is again that number. Let's see what happens with 128. So this is 1. 1 divided by 2 is 1/2, and then I would have 127.5. But let's say that my operation is rounding down. So I have again 127, and then what happens with this one? So the difference is 2 divided by 2 is 1, then I get 128, and you could construct the whole table. Okay, so this is I, this is J. What happens with K? So K is the same equation there, but now multiplied by 2. Okay, so 127 will also go to 127. What about this 127? Goes to 127. What about this one? This one, the difference is 1. You multiply by 2, and you add 127. So this goes to 129. And this goes again to 129. Now you see the holes. There is no way in this operation I can get 128. Okay. So increasing the contrast, decreasing the contrast don't create problems. So I have some rounding problem. I have it here. So two elements were going to the same value. So when I decrease the contrast, I'm adding beams. And when I'm increasing the contrast, I'm creating holes in the histogram. And then we have the opposite of sequence. So you take the original, first you expand, and then when you expand, you will have to saturate, and then you decrease. But when you decrease, and you don't have holes, because decreasing don't create holes. The holes are created when you expand. And you see that these two histograms are not exactly the same. So here I have one big saturation, here I have kind of different saturation to this one. And here I am also saturating. So it looks quite different. So actually the comparison, the right comparison is this one with this one, not with this. But here you see that. So all these saturated pixels are all these ones here, and all these ones that go to here. And this one should be similar to this one. And somehow they resemble, but they're not exactly the same. So if you want, you can compare these two too. So this is first you increase. So let's draw it. So you have an input image. You have an input image. First, you multiply by half. and then you divide, multiply by 2, you have k, and on the other side, you have first you multiply by 2, and then you divide by 2. And these K1 and K2, they are not the same. K1 is different from K2. We have seen at the level of histograms, the two histograms look different, so the two functions are also different. So these two operators do not commute. Why do not commute? Why do they not commute?
Or we are losing values when mapping them.
Yeah, but in general, when can you commute systems?
That's invertible.
When they not invertible, when they are linear. So there must be some non-linearity here. So what is the non-linearity? You see that, so it was decreased contrast, very stuff. So in decreased contrast, there is no non-linearity. This transformation is linear, but this one is not linear. There is a kind of if. So if you have an if, you can have several cases. The several cases are non-linear, and they are not invertible either. Okay? So you have lost information because these functions are not invertible. Even this one is invertible or not. As it is written here, this function is invertible. So if I tell you x, you give, so I tell you x, you get y. I tell you y, can you get x?
Yes.
Yeah. Yes, in real numbers operations. If you are using integer values, then it is not invertible. We saw it here. So here we have two values going to the same. So that is not invertible. So if you are operating, if you were allowed to write 127.5, then it is invertible. But if you're not allowed to write that, then it is not invertible. Actually, the rounding is a non-linear or the linear operator. Non-linear operator. Very good. So they don't commute. So they are not the same. Doing one and then the second, or second and then the one. Very good. And then this guy likes making all kinds of comparisons. So then he's comparing the original with the low contrast and the low contrast restored, and then computing the difference of this one with respect to the original. And then, but there is something interesting here, that is this one. Low contrast restored compared to the original. So the difference is just kind of noise. There is a little bit of a structure there. So we have lost a bit of information, but it is not terminal. What about this one? So this one, when you compute this one, first you were increasing the contrast and then saturating points and then decreasing. Now you have lost a lot of information, and we see the saturation. So we see that some of the pixels are unnaturally bright. These ones are unnaturally bright, and the difference is this one. So this one is losing a lot of information. This one is losing information, but nothing really terrible. So when you see in an image, you see a structure, you see a lot of structure, details related to the original image. That is a big information loss. Okay, then we have this operation, increase gamma. So what is increase gamma? So increase gamma is this operation, and we recognize again the same kind of tricks. So first we apply some change of coordinates. So now the change of coordinates is not a shift, it is a compression. So we compress the coordinate system, then we apply some operation, and then we undo. So it is the same kind of structure with the shift, but now with compression of the axis. So if we divide by 255, this number has to be between 0 and 1. Then we are computing the gamma root of that number, and then scaling it back to 0 to 55. And here we have an example with some gamma larger than 1. So it looks like that. So now the question, is it increasing or decreasing the contrast? Increasing. Why?
No, actually, it's decreasing.
Sorry?
It's actually decreasing the contrast.
Decreasing. Why?
Because it's making the curve more smooth. Like there's less difference.
There is a lot of smoothness here. So it is not a smoothness. So the contrast was related to the slope. Actually, it is doing both. It is increasing the contrast and decreasing the contrast. The slope up to this point is larger than 1, and then the slope from this point is smaller than 1. So it is increasing the contrast of the dark values and decreasing the contrast of the bright values. So it is doing both. And this is called increased gamma. And then we have decreased gamma, that the transformation is the same, but with gamma smaller than 1. And then we have the opposite. Okay, so here we are decreasing the contrast. Here we are increasing the contrast. And then some more examples. So this was the original, increased gamma, decreased gamma. And then we recognize already the patterns that we expect. So where you are decreasing the contrast, where you are increasing the contrast, so you are stretching the histogram, then you are creating holes in the histogram. And in those places where you are decreasing the contrast, so you're putting beams together into the same value. So here you have these spikes because of the same reason why we have these two numbers going to here. So the beam in the histogram of this 127 and the beam in the original histogram 128 will add up in the output in the same beam. So these spikes are coming from decreasing contrast, and these ones from increasing contrast. And the same here for the other. Yeah. Any question? Yeah.
So kind of like increasing dark values means that it decreases the contrast in there.
Yeah. So where the slope is smaller than 1, it will decrease contrast. So here the slope is smaller than 1, and then it accelerates. So here it is larger than 1, here it is smaller. So here there is a decrease, and here there is an increase. Very good. Yeah, this is a reminder of what the histogram is and the connection to the probability density function, the normalized histogram, the cumulative. So all this is a reminder from the last week. Yeah. So, and here we have for a given image, and we are computing the histogram for the luminance, for instance. So we have the PDF. The PDF is the probability. So let's remind that. So we have PDF. I for a gray value, it is the probability that I takes value G. And PDF, sorry, not PDF, but CDF. CDF is the cumulative one. CDF that is probability of I of R smaller or equal G. Okay, so if I take a pixel at random what is the probability that it takes value G, that is the PDF. And the other one is, if I take a pixel at random, what is the probability that it has a value smaller or equal to G? Very good. So here we have the PDF. When you see as expected, the PDF should have very small values. So the probability, the highest probability is something like 1% or something like that. And the capital PDF or the CDF is the cumulative density function. So probability of being smaller or equal a value. So smaller or equal 40, it is 0 because there is nothing below 40. And then it continuously growing up to 1. So the probability of taking a pixel at random and having a value smaller or equal to 55 is 1. All of them are smaller or equal to 55. So this has to go to 1. And it goes increasingly, so it is monotonically increasing. So if this function cannot go down, it has to stay or go up. Okay, so yeah. So now we will define the histogram equalization as another point operation. This point operation will take the gray value in a band. It will go through the CDF and then scale it back to 55. Okay, so let's see the reason. So the reason, this is just to compare with the minimum and maximum. That is a different operation. So let's say that we have this value image, and then this is the histogram equalized value image. So what this is doing is, you take this image, you compute the PDF. From the PDF, you can compute the CDF. And now this is your function. This is your lookup table. So this lookup table, I have a value here, let's say a value 100. So a value 100, I go to the CDF, and a value 100 has to go to 0.55. So then I multiply by 255, so I scale it back to 255, and that is my new value. Okay, so that is the value that I will put here, and the same for all the other pictures. Okay, so you see that it looks a little bit like artificial image. And does the information contained here is the same as the one here? Have you lost, except for the rounding we don't care. So except for the rounding, is this function invertible? It is. It is invertible. It is separating here. It is separating here for no pixels. No pixels were there. So if you are given this image, you can't absolutely recover this one. It's invertible. It's the lookup table, so the CDF multiplied by 255. And then here is some nice representation of it. We will discuss this. Okay, let me make the comment. So here we have equally spaced beams. Then what we see is that in this area, we are increasing the contrast. And in this area, we are decreasing the contrast. So the output here, the difference is much smaller. And here the differences are bigger. Here the slope is larger than 1. Here the slope is smaller than 1. And the reasoning is, okay, if you have a lot of pixels in this area, try to stretch the contrast so that you separate the values and you see them better. If you have very few pixels here, we have very few pixels here compared to this one. So if you have very few pixels there, you are sacrificing contrast, and you are sacrificing contrast where there are very few pixels. So very few pixels will be affected by that. So here the contrast increase or decrease depends on the number of pixels that are there. So where you have pixels, where you have many ones, try to increase the contrast. Where you don't have so many, you sacrifice contrast. Okay, so let's make a break. Very good. Then the next. So yeah, now we can look at the histogram of the original image, the histogram of the equalized image, and we already recognize the kind of patterns that we already know. So the holes created by stretching the contrast and the spikes caused by adding, by decreasing contrast. Yeah, so we have an original image, luminance image, the luminance histogram, the luminance CDF, the lookup table. So the difference between the CDF and the lookup table is simply multiplying by 255. So we multiply by 255. And then we equalize the luminance using this lookup table, and again the same kind of patterns that we saw before, the holes created by stretching the contrast and the spikes caused by decreasing contrast. And yeah, and this is the luminance and the equalized luminance. And there are some regions that yeah, in general, overall, I would say there are some regions that have gained. So these trees here, you see them better there. But there are some regions that have been sacrificed. So all these bright areas, now they are much more saturated, they are more difficult to see. So whatever was bright, now it is hard to see. Whatever was dark, now you see it better. And let's do it with color images. So you have a color image, you compute the histogram of each one of the bands. Then you can compute the CDF of each one of the bands. And the lookup tables. And you equalize each one of the bands according to its own CDF. And this is the result. So you can compare the original. This was original here. So original compared to equalized. So it is true that we are using better the dynamic range. We are using the whole dynamic range. Actually, the histogram equalization doesn't succeed, but it tries to make the histogram more uniform. So we can see that here in the first cases. So for instance here, so you see there is a big difference between the luminance in some region and the luminance in some other region. This one is much more uniform. It is not completely flat, but it is much more uniform. So yeah, this was the result. Yeah, this one here. And what we see here is that somehow the colors look natural. But we will see later a better way of equalizing with color patterns. Okay, so we see there the two at the same time. Then what we will do is, okay, we are back to the original, with the original PDFs, the color CDFs, and we will compute the lookup table from the luminance. So you take the luminance, you compute the equalization of the equalization transformation to the luminance channel, but you use that channel for the three bands. So it is not like here. So here we were applying three different lookup tables to each one of the bands. Now we will apply the same lookup table to all bands. And this lookup table is coming from the luminance. And this is the result. Okay, so it is now a bit better than the each one independently. So somehow what we have coupled is all the bands together so that if they shift consistently. They shift the three at the same time. Then there is another useful operation that is this histogram matching. The one we have seen before is called histogram equalization. This histogram matching, we will see it in more detail, but I think it is useful to see the final result to know why we want this thing. So yeah, one example is this one. Okay, so let's say that we have two pictures of the same garden, a different region of the garden. So you see, there's one picture, there's another picture, but this one, the camera was somehow saturated, and these colors are unnatural. These look like much more natural colors. Okay, so now the question is, can I transform these colors such that the histogram of this is more similar to the histogram of this? That is what we are trying to solve. And the answer is yes. And once you do it, this is what you get. Okay, so the saturated camera, now you can fully recover the natural colors. But you need an example. So what I'm telling the computer is, okay, take the histogram of the original image here, take this histogram and forget about it and try to get a histogram more similar to this. And here we have another example. So let's say that you have two cameras looking at the same object, and again, the colors do not match. And if you want to combine the two, then you can actually transform one of them so that it looks the other one. Okay, so this is what we want to get. Now let's see how to get that. Okay, so let's go back to this histogram matching. So we want to do that for the examples I showed you. Let's see how we can do it. So the key thing will be matching percentiles. Okay, so this is the CDF of one of the images, I. This is the CDF of the other image, J. And let's say that in the input image, I have a value 5. So a value 5, I can ask, what is the probability of taking a value 5 or smaller in image I? So 5 or smaller in image I, this is the CDF. It is, let's say, 0.65. Okay, so now I have to look for a value in J such that the probability of being smaller than that value is also 65. So all these values, they don't get to 65. Even 9 doesn't get to 65, but 10 does. So 10 is above 65. It is the first value that is above 65. And then that will be my substitution. So I will substitute 5 by 10. So it is, I will make the change such that the probability of having a value smaller than GI is 5, is larger than the probability of having a value GJ minus 1, so the 9. So 65 has to be, 0.65 has to be larger than this one. Let's say that this one is 0.6. So it is larger than 0.6, but 0.65 is smaller than this one, but let's say it is 0.66. Okay, so you have to find this GI and this GJ that fulfills this condition. Actually, I don't have to invent the numbers out here. Very good. Then this value will be substituted by that, and that is your lookup table. Once you have the lookup table, you simply apply. Any question to this one? Okay, so let's try to formalize that one. So I have a value I. Have a value I. This is my gray value. Let's use the same notation as they. So I have the gray value I. I compute what is the CDF of that. So I compute the CDF I that. Okay, so let's put numbers to this so you're not lost. This is 5. This in my example was 0.65. And now I look for the J value such that it is this one. Okay, so that one is CDF minus 1 distinct. And this is 10. Okay, so let's see why. So CDF goes from gray to probabilities. CDF minus 1 is the inverse of that function, not 1 over the value, but the inverse function. If we have y equals x squared, and this is f of x, then f minus 1 of x is the square root of it. Okay, so inverse in this sense, not 1 over f. Okay, so we started with the gray, we go to probabilities, and then this function takes probabilities and returns another gray. And I will transform this 5 into this 10. Okay. And then this condition is simply because in general, you will not find exactly the same value. But the goal, if you could, would be this one. Okay, very good. Yeah, so now this is the serial code to get that. We don't care about the serial code. And here's some example. So we have this image, we have this PDF, and this image has only 16 intensity values. Actually, you can see that here. You see that it goes in the steps. So you have only 16 values so that we can track the whole histogram. And then this is the CDF, and this is the PDF of a different image. This is the CDF. And then I construct my lookup table. Yeah, this is the MATLAB code for that. And this is the same idea. So as we said before. So for every value, I have to look what is the probability of having a value smaller or equal to that one. And then I do the inverse of the target CDF to get what is the value that what is the gray value that has a similar probability. And then that gives you this transformation matrix. And you see that this transformation matrix is also monotonic. So it can only increase or stay. Okay, then this is MATLAB code for that. But so this was the input, this was the target, this was the lookup table, and then when you apply this lookup table to the input image, this is what you get. So and we understand here this histogram matching principle. So this lookup table transforms this histogram into something that is not exactly this one, but it is the most similar you can get to it. And here you have the result. So this was our original image, this was the target, and now this is the final result. So now the histogram of this one is more similar to the histogram of this. And we see that that is true in a sense, no? So this was darker, and now in this dark image, we have made it brighter because this image is also brighter. And we could see that in the histogram. So this histogram is mostly bright values, while this histogram is more, it has a lot of bright values, but it has the tail, the importance of this area with respect to this is much higher than the importance of this area with respect to this. Okay. Then we can do it with the full image, not only 16 values, all the channels. So we have the PDF of each one of the channels, the luminosity, all the CDFs, and yeah, a different image, all the PDFs, all the CDFs. And here we have the original, the target, and this one in which we have only remapped the luminosity. Okay, so we have somehow transformed the luminosity. So using the CDF of the luminosity, the CDF of the luminosity here. So we compute the lookup table with that, and we apply that lookup table to all the channels. So that is what we have done. So here you have the different, so CDF of one, CDF of the other, the lookup table, and the CDF of the final one, which is not exactly as the target, but it is more similar than it was before. Very good. And then we can see how do the new PDFs look like. So these were the PDFs of the original, and after the remapping, and we recognize the kind of patterns that we already know. So this is increasing contrast, these spikes are decreasing contrast, and so on. Very good. This is all kind of comparisons. Any question this part? Okay, so let's see another example. So this example, so we saw histogram equalization. So histogram equalization of each one of the bands having its own lookup table based on the CDF. It was this one, and it was a little bit weird. And then we use the luminance to make a transformation, and we said, okay, there are these saturation effects, but now the colors relationships, they are more natural than in here. So here there are some kind of artificial blues and so on. Now we can do something different because I can do the histogram matching of each one of the bands to the luminance. Okay, so and this is my new lookup table. So my new lookup table is the CDF of each one of the bands, and then I'm matching it to the luminance. You see the kind of equation that I wrote here, right? Okay, so, and now it is even better. So the relationship is even better. The relationship between colors. We don't see very unnatural colors there. So this is a description of what we just did. Okay, and then another example. So equalization of a color image via luminance matching. So you can compute the histogram of each one of the channels, the luminance. and then the CDF of each one of the channels and the luminance, and then the equalization lookup table. For each channel is slightly different because the formula depends on the band. So each one of the bands will have its own lookup table, its own transformation. Okay. And then the histogram of the results and all that. Okay, and then another example. So we have this image. This one is kind of red. So you transform this one, and it becomes again kind of red. All the PDFs and CDFs and everything from everyone, and all the histograms. Yeah, this is quite repetitive. And now we see the example that I gave you at the beginning. So the cameras are mismatched. So this camera is miscalibrated. And because you know that this one is well calibrated, you may want the histogram of this to match this one. That is what you get through this technology, through these operations. And actually, you can see that the lookup tables, they are quite different. And so the green lookup table is quite different from the red and blue. And actually, it was the red one that was somehow miscalibrated. So it makes sense that it is the one that is most effective. This is the result. The same for this one. So this one, there are not such big differences between the three. They're not the same, but more or less they look kind of similar. And then you get this one. Very good. Any question?